We already learned that when studied using three-dimensional cylindrical coordinate system, the acceleration of the particle has three components: AR along the radial direction, a theta along the transverse direction, and a z along the z direction, which is the same as the rectangular coordinate system. Therefore, the equation of motion, Newton's second law, can be rewritten into three scalar equations that the resultant force along the r, theta, or z direction equals to m times acceleration along the r, theta, and z direction respectively. For a 2D problem, the 3D cylindrical coordinate system reduces to the 2D polar coordinate system, and the acceleration only has AR and A theta two components, and the vector form of the equation of motion can be rewritten into two scalar equations that the resultant force along the radial direction equals to the mass times acceleration along the radial direction, and the resultant force along the transverse direction equals to ma theta. Once again, AR and A theta can be evaluated by these two equations. There's something we need to watch out for. We know that we can always draw a tangent line anywhere along this path. But normally, this line does not superimpose with either the r-axis or the theta axis. However, if we do know the function of this path, we can determine this angle psi, which equals to arctangent r over dr d theta. This angle psi is made by the positive radial axis and the tangent line. And just like the sign convention for any angles we use in this class, positive angle indicates counterclockwise rotation. Let's look at this example. There's a 1 kilogram ball being pushed by a rod to move in a horizontal, grooved, smooth lot. Horizontal indicates that for this problem, we do not need to consider the weight. And also, smooth slot indicates that we do not need to consider friction. It starts from when theta equals to 0 degree, and we need to determine the force the rod exerts on the ball at theta equals to 15 degree. If at this instant, the rod moves at an angular speed of 1 radian per second and an angular acceleration of 2 radian per second squared. The ball is only in contact with the outer side of the slot. We're going to use the polar coordinates to solve this problem. We need to first set up our coordinate system. We choose this to be our origin, this line to be the reference line since it corresponds to when theta equals to 0 degree. Therefore, at the instant that theta equals to 15 degree, this is our radial axis and this is our transverse axis. And now we're ready to draw the free body diagram of the ball at this instant. So it is subjected to the force exerted by the rod, which is perpendicular to the rod. Therefore, it is already in the transverse direction. Also, it is subjected to the force exerted by the slot. And because this ball is only in contact with the outer side of the slot, therefore the normal force is normal to this path, perpendicular to this tangent line, pointing in this direction. And since we are only considering the horizontal plane where the motion happens, we do not need to consider the weight force. Therefore, this completes the free body diagram. And we draw a kinetic diagram showing the acceleration components along the r and theta direction. And now, before we can write our equation of motion, we need to find out the direction of the normal force so that we can resolve it into the corresponding r and theta components. Remember, the angle made by the positive radial direction and the tangent line, psi, can be evaluated by this equation, and since in this case we do know the function of the path, r equals to 2 times cosine theta, therefore dr d theta equals to negative 2 sine theta at theta equals to 15 degree, psi can be evaluated to be negative 75 degree, which indicates a clockwise rotation of 75 degree. And now we are ready to write the equations of motion. Resultant force along the radial r direction equals to negative n times sine 75 degree. That equals to m, the mass of the ball, times the acceleration along the radial direction. And the resultant force along the transverse direction, theta direction, equals to F minus n cosine 75 degree equals to m a theta. Now both n and f are unknowns, therefore we need to first find out what a r and a theta are, and then we can solve for our unknowns. Since we know the function of the path, r equals to 2 times cosine theta, therefore r dot, which is dr dt, equals to, by applying chain rule, dr d theta times d theta dt. Dr d theta is negative 2 sine theta. D theta dt is simply the angular velocity theta dot. And then r double dot, the second time derivative of r, equals to, by applying the product rule first, and then chain rule, it becomes this. Here, theta double dot is the angular acceleration. And now we are ready to do the evaluation. At theta equals to 15 degree, theta dot is given 1 radian per second. Theta double dot, angular acceleration, 2 radian per second squared. Therefore, r equals to 2 cosine theta, which is 1.932 in the unit of meter. R dot equals to this, which is negative 0.5176 in the unit of meter per second. R double dot equals to this, negative 2.967 in the unit of meter per second squared. Therefore, the radial and transverse accelerations can be evaluated by these two equations to be these values, both in the unit of meter per second squared. Now, in the two equations of motion, we know mass, which is 1 kilogram. We know the acceleration along the radial and transverse direction. Therefore, the only two unknowns are n and f, and they can be solved from these two equations to be 5.07 Newton and 4.14 Newton. And this is our answer to this question.